right. Thank you so much for that introduction. So hi everyone, my name is Daniel and I'm a graduate student at the University of Rochester over in Western New York. And today I'm excited to share with all of you how we're using computer vision techniques and machine learning, or AI as it's more commonly known as these days, to perform a label-free analysis of our leukocyte trafficking dynamics using a microvascular mimetic. So in our lab, we study sepsis, which is defined as a dysregulated systemic inflammatory and immune response to microbial invasion that ultimately results in the circulation of bacterial products and inflammatory cytokines throughout the body. So this causes organs distant from an infection focus to behave as though they too are infected, leading to a cascading cytokine storm that promotes an overactive immune response. Ultimately, this leads to organ damage, death, and failure in many cases. So we're primarily interested in understanding neutrophil transmigration in response to disease endothelium and sepsis. Now, neutrophils are the most abundant leukocyte in the body, and they're implicated in septic-mediated tissue damage due to impaired migration. So when systemically stimulated by these circulating inflammatory factors and bacterial products, septic neutrophils exhibit dysregulated transmigration towards an infection focus via decreased IL-8 sensitivity, while simultaneously sequestering inside tissues and organs via increased MCP1 sensitivity. So to better study the interplay between septic neutrophils and endothelial barriers, in our lab we've created the MicroSim platform, which stands for microchip devices featuring ultra-thin nanoporous silicon nitride membranes. These small microfluidic devices feature multiple format configurations, including a transwell-like format with a small well as a flow cell configuration. And there's plenty more. If you want to learn more about it, you can talk with my boss who's sitting over there. But generally speaking, a microsim device features two channels or two compartments separated by this freestanding silicon nitride membrane that I pictured here in the middle. And this is very thin. It's less than 100 nanometers thick, has a pore size of about 50 nanometers on average, and a porosity of about 20%. So what this gives us is a membrane system that gives high optical clarity, it's extremely permeable, and it allows us to create these distinct tissue and blood side compartments in our microphysiological system to better mimic endothelial physiology. So what this gives us then is an ability to perform these reductionist experiments where we can perform a tissue-sided stimulation or a blood-side stimulation and then observe a subsequent response from our endothelial cells and, coming up, our immune cells. So all of these properties together indeed do facilitate a multitude of in situ experimental approaches, and we also have the ability to take advantage of multiple imaging modalities. So for our studies involving neutrophils and transmigrating disease endothelium, we utilize high-resolution phase contrast microscopy. And here's an example of these studies. So in these videos, you're seeing neutrophils crawling on an endothelial interface composed of human umbilical vein endothelial cells. Now note, these neutrophils are primarily isolated from human blood, so they're not iPSC derived, they're actually coming from people, usually me sometimes, but it's okay, it's IRB approved, it's fine. We had approval for it, but you have to get neutrophils from somewhere. But on the video on the right, what you see is there's neutrophils engaging in this unique morphological transformation. It's a little hard to see, but generally speaking, you can see them going from this white shape to a darker black shape. And what's happening here is that we've incorporated a potent neutrophil chemoattractant into the tissue side of our device down over, actually, let me see if I can, there it is, perfect. So in the tissue side of the device, we've incorporated FMLP, which solicits a concentration gradient that the neutrophils can then respond to. So these videos are a bit abstract without contextual and spatial information. So to better understand how neutrophils navigate the endothelial cell monolayer in a microsim device, we typically break up neutrophil transmigration into three distinct phases that are linked to their morphological profile in a phase contrast microscopy. So in panel A, we can see our neutrophils manifest as these bright white round shapes, and we've outlined that in green, and this typically indicates that they're above the endothelium. But when neutrophils become activated, they quickly take on these amorphous morphologies and begin shifting to this grayer color scheme or contrast that matches the endothelial background, and that's outlined in blue. And then finally, upon full transmigration, we see neutrophils manifest as these phase dark or very dark gray contrast schemes, which is outlined in red. So for the rest of this talk, just note that when we refer to something as apical, that means it's above the endothelial cell monolayer, and basal typically refers to something underneath the endothelial cell monolayer, and above our nanoporous membrane substrate. So in our videos, there are a lot of neutrophils and dynamic activity occurring, and extracting useful information manually is extremely difficult. If you want bulk metrics of activity, you would have to actually go and manually measure what each neutrophil is doing at a given point in time, and that's difficult. So our goal for this project then was to develop and validate a set of computational analysis tools that give us time-resolved data on the number of neutrophils present in a video frame of view, and what they're doing. So if they're apically oriented, they're probing the endothelial cell monolayer, or if they've already transmigrated, as well as trafficking metrics such as how fast they're moving and general metrics of activity. Ultimately, we're creating a high-throughput analysis tool that can help elucidate neutrophil trafficking dynamics on our surfaces here. And the key thing is that we're doing this with a two-dimensional phase contrast modality. So for normal image analysis applications, a simple algorithmic approach may be feasible. However, cell tracking presents a significantly more challenging environment. So while high contrast images can be used to effectively delineate one cell from another, such as in this example video, cell tracking difficulty increases when you have more challenging environments, such as a low contrast video, a crowded field with a monolayer or a co-culture, the target of interest that you're imaging for, as well as the underlying imaging modality and optics present in your system. In our work with phase contrast microscopy, our co-cultures consisting of HUVECs and neutrophils have already presented significant challenges in detection. So back over to panel A, we've actually been able to isolate these neutrophils fairly simply with conventional image analysis algorithms, mainly because these neutrophils have such high contrast with the endothelial background. But as neutrophils activate and they begin shifting to these grayer color schemes that more accurately match the endothelium, it becomes more difficult to follow them with conventional algorithms. And even this phase dark morphology here actually matches organelles and nuclei of our HUVECs, posing another challenge differentiating them from one another. So since normal image analysis algorithms have failed to delineate probing and transmigrated neutrophils in our phase contrast videos, we've enhanced our detection capabilities by turning to advanced machine learning techniques. And in our case, we utilized a tandem approach of a random forest feeding into a convolutional neural network to extract relevant data and information from our neutrophils and for the creation of our leukocyte analysis tool. Just to be brief, random forests work by combining the output of multiple decision trees into a consensus. So they're pretty powerful because they have low variance, low bias, and they have a low risk of overfitting. And that's excellent when you're utilizing data sets that have one overrepresented class. And if you look at the videos I just showed you, the endothelial cells make up the vast majority of our surface area in a device. Next, the convolutional neural network works by essentially applying linear algebra or image convolutions to an input, ultimately searching for features of interest, like an edge in the cell culture case, and then classifying that into a predefined class of interest. So to create our tool, what we then did was we took preliminary experimental data for our model training. So we performed video recordings for trafficking studies using a negative control and a positive control approach, where negative control is an untreated device and a positive control simply incorporates FMLP into the bottom channel so that we can have that gradient that neutrophils respond to. So when our devices were confluent with our HUVEC monolayers, we seeded them with 3 million neutrophils per milliliter and then began recording for 30 minutes in phase contrast at a frame rate of about 1 frame every 4 seconds. Now note, we chose 3 million neutrophils per milliliter because that's a physiological value for neutrophils in the human body. So 3 million neutrophils per milliliter of blood, for healthy humans at least. So select frames from these videos then underwent ground truth labeling for our semantic segmentation algorithm, which really is as simple as using a paintbrush tool and then painting over and creating a mask, delineating what class is what for each of our neutrophils. We labeled for 4 classes based on both neutrophil behavior, so apical, probing, and basal for our neutrophils, and then a 4th class delineating endothelial cells just to use as a background condition. So after labeling, we trained the model over and over again and added more labels as needed until we achieved a satisfactory error rate of about 2.7%, which was measured via out-of-bag error, which is standard for a random forest. The output data from this process then is a high contrast color map, which was then used to give us information for neutrophil state and trafficking. And here's an example of a color map. So what we did was we actually lowered the opacity of the color map and then overlaid it onto our phase contrast video to bring better context for what's going on. So the semantic segmentation algorithm gives us high contrast information, but we still need to actually analyze what we're seeing. And one of the problems that constantly occurs in these videos is, 1, the neutrophils take these rather unusual morphologies, but 2, they collide with each other and they crawl over each other. So in order to delineate these events, we needed to find out what was the difference between a single neutrophil and a cluster of neutrophils. So we fed this data from the segmentation maps into a feature extraction algorithm that took out everything that looked like a neutrophil and a cluster, and this was a conventional algorithm that worked really well because we were able to delete the entire background of endothelial cells. From there, we did additional ground truth labeling to delineate single neutrophils from clusters, and we fed it all into a convolutional neural network based off of LENet5, which for those of you who don't know this, LENet5 was originally designed to analyze handwritten numbers, and somehow it can analyze neutrophils. So it's really fun when you can do that kind of training. So what we ended up having then was a final count where we used a typical split of about 90% training, 10% validation, and had a rough error rate of about 1.2%. And that gave us the ability to both count neutrophils and then see how many of them were transmigrating. So in summary, the full pathway looks like this. We can take an experimental video with a phase contrast microscopy setup, feed it into a semantic segmentation algorithm, and then feed that information into a convolutional neural network and get relevant parameters. So one thing you'll notice that there are red circles in this video. Those were just used to mark neutrophils. Occasionally when neutrophils collide, you might see a larger red circle, but in script, we were able to delineate them individually. This is just for showcasing purposes. Okay, so then the machine learning workflow data sets were then compared to manual transmigration and population counting. So where population counts and number of neutrophils were tabulated once every 30 frames for each of the videos that we had. Our success metrics that we considered were a population count with less than 10% error rate, and for considering transmigration, statistical parity between our manual counting and our model counting. So first we looked at counting. For validating our model, we looked at the distribution of all automated neutrophil counts in a video frame and found that it was similar to our manual counts. And then when we look at both negative and positive control studies individually, we both see that the automated process meets our criteria of sub 10% error in counting. You'll note that the positive control studies have a higher overall error rate than the negative control ones, and that's likely due to the fact that the neutrophils take these more difficult to detect amorphous morphologies as they become activated. Also, when looking at individual replicates, we can see that population counts are tightly correlated between our model groups and our manual counting. Further, the low variability across our 30-minute experiments indicates that our neutrophil populations are fairly consistent across an experiment. So what this means is that the neutrophil populations in our device are typically homogeneously distributed, and that if a neutrophil leaves a recording field of view, it's usually replaced by one coming in. And this is best exemplified by viewing temporal population data, where the black dots represent manual counts and the orange line represents what the model sees. So we can see here for both a positive control and a negative control study, there's population stability over the course of our experiment. And just so you remember, I mentioned that we have XY parity, but what about the Z direction? Well, think about the way our devices are designed. We have this nanoporous substrate that only has 50 nanometer pores. So even if a neutrophil wants to chase the FMLP that it's sensing in the bottom channel, neutrophils can't crawl through 50 nanometer pores. So that's how we achieve population stability, and there's no loss when observed via imaging. So for assessing transmigration ratios, our studies show that both negative and positive control groups are capable of being analyzed by our model. We performed another distribution analysis just to look at the overall distributions of what our model was seeing versus what our manual counting was, and we found that the groups were statistically similar. One thing that's important to note was also something that we expected. The positive control group solicited a higher transmigratory response than our negative control. And again, if we look at individual replicates, this is fairly simply exemplified. So here we can see no difference between model counting versus manual counting. So even when neutrophils change their morphologies into these more amorphous shapes when activated, we're still able to monitor their trafficking behavior. And then lastly, when we calculated residuals between our model and manual groups, we found them to be evenly dispersed for both population counting and transmigration analysis. So this indicates to us, at least, that the model is not biased towards overcounting or undercounting, and typically will have a low false positive and negative rate. So the computational process I described earlier can generate multiple statistics on our neutrophils, including geometric properties such as eccentricity or area. But the most important data set that we can generate with our workflow is collecting all the centroids for each detected neutrophil. So what we did then is we took these centroids and used a nearest neighbor linking approach to create a tracking algorithm. And we optimize it with additional logic to correct for aberrant track making, as well as mitigating errors. But once all these tracks are collected, and I guess I'm in the way for this, we would calculate mean square displacement for each trajectory and then fit it to this equation right here that's known as the Ahmad equation. The key thing that you need to know from this is that this lets us do a curve fit for extracting speed and persistence for each trajectory that was in our video. And speed is a fairly self-explanatory value, while persistence is the capability of a particle, or in this case a neutrophil, to maintain a trajectory of motion before completely turning around. So an example report from this process looks like this. We can take the machine learning generated centroids, apply tracking logic, and generate XY scatter plots like we see in this video. We can then calculate mean square displacement and then fit it to the curve fit that I mentioned previously, and then extract parameters that are relevant for our studies in a bulk manner. So one important thing I want to note is that we actually are not capable of following a single neutrophil from start to finish in a study. And that's an extremely difficult problem that we're working on. But typically what happens is we generate multiple fragmented trajectories, but that still gives us an ability to assess what neutrophils are doing in a bulk manner on these devices. So then when we talk about assessing the accuracy of our tracking, what we did was we compared both speed and persistence across our negative and positive control and multiple groups generated from our model. So the first group that we created was all trajectories with a track length greater than 100, or 100 frames or 400 seconds. The second group of the analysis utilized the longest 15 tracks created by the model. Remember, 15 was the number of neutrophils that were manually tracked. And then lastly, we took 15 random tracks. And across the board, between all comparisons, we see that there's no significant difference between speed and persistence measurements for both our negative control and our positive control when comparing manual and model-generated parameters. So one thing that we also did just to make sure was, as an additional point of comparison, there was a lot of variability in persistence over here, so we made another analogous measurement called chemotactic index or meandering index, which is not done from a curve fit and is instead distance over path length. And we found that that was statistically similar for both negative and positive controls as well. So ultimately, as a summary, our model is able to take neutrophil experiments and provide numerous statistics. Here we see that stimulated neutrophils, when compared to non-stimulated ones, engage in more transmigration. They're faster, they're more persistent, and then they have a higher chemotactic index as a result. And these are all values that correlate with literature and were all derived from our model. Okay, so just to be quick, we did want to do a quick showcase of what the model is capable of. Remember, we're studying sepsis, and with a validated model, we decided to see if we could generate relevant statistics on a septic-like condition. So we took an equimolar combination of TNF-alpha, IFN gamma, and IL-1 beta set to 50 picogram per mil, which is derived from sepsis literature, and then stimulated devices either on the blood side or on the tissue side to mimic circulating inflammation and tissue-sided inflammation respectively, just to get a baseline comparison and see if there was a differential neutrophil response. And this is essentially what we found. So when we look at our results for neutrophil transmigration in response to a cytomix stimulation, we can see that there's already differences. First, the apical-sided or the blood-sided cytomix stimulation results in a mitigated neutrophil transmigration that's similar to our negative control. But if we stimulate on the tissue side or the basal compartment, we see a massive amount of transmigration that dwarfs all of our measured categories. And there's more data on this, but for now I just wanted to show a baseline so that you can appreciate what our model is capable of. Okay, so in summary, we have a machine learning-based approach for semi-automated image analysis. We're continuously developing it and are hoping to expand its usefulness to other endothelial cell types as well as other immune cell types for simple transmigration studies. In the future, we're hoping that this can be used for rapid analysis of video microscopy data. So in summary, this is all of my lab members. I think I have everyone. If I'm missing someone, I apologize. We have a lot of people. But yeah, so everyone's been pretty instrumental in helping me out in multiple ways. So I just wanted to thank everyone. But more importantly, my lab mates are also presenting soon. So Raquel will be presenting on another function of the device that we use, the microsim device. And Molly will be talking about reproducibility. So please go to their sessions. We also have many posters present, although I think most folks have already presented. So yeah, that's all I got.
Thanks, Daniel. Really impressive, and it really shows what AI can do to set the stage for further progress. Yeah. Time for one question. Yeah.
Did you try to train on the time derivative of your video so you could subtract the background and have just like the contours of your cells to work with?
No, so we haven't worked on that yet. We wanted to make a more straightforward approach, so it's simple right now, but we're hoping to expand in that direction as well.
Thanks.
Thank you.
Okay.
Great talk.